Chuck.
Hey, Neil.
I got another one for you. You know,
All
these never end. You know,
good.
I got another one.
It's a good thing that they're going on. People love these.
So I thought maybe we'd talk about hot and cold.
All right, hot and cold.
Hot and cold.
So we're discussing my marriage. What's happening?
Okay.
What is going on?
Hot and
here?
cold. So a couple of things. You realize there's no real upper limit to how hot you can make something. Right?
Okay.
In fact, the early universe was like trillions of degrees. You just can keep going. If you concentrate enough energy into a small enough volume, you can just keep increasing the temperature essentially without limit.
Wow.
But you can only do that because such a thing as heat exists. You can just keep adding more heat.
I got you.
Right? If you have something,
Right.
you just have
you
more
can
of it.
Always pile it on.
Pile it on. Okay.
Right.
So now, if heat exists and cold does not exist, then what happens when you just start taking away the heat?
So wait a minute. Are we defining? Is the definition of cold the absence of heat? Is that what it is?
Let me just. Yes.
Okay.
Yes. Okay. Yes. So I got heat. I can add as much of it as I want, but if I start taking it away, the temperature begins to drop. Right. Okay. So now there comes a point. The heat energy, I should say. So there comes a point as you keep removing it.
Right.
Where then there's no heat left to remove.
Right.
Okay. And there's a guy named Lord Kelvin, a physicist, who, let me hear you imitate the peerage.
Of course, Lord Kelvin.
Lord Kelvin.
Indeed. Today I believe I shall endeavor to find out exactly what happens when I remove heat.
So he explored what would happen if you remove all the heat from something. If you remove all the heat, what temperature should you call that?
I would say the no heat temperature.
The no heat temperature.
No, it's the absolute cold.
So what
Absolute
temperature
cold.
would you, if you had to give a number to it, what number would it be?
Zero.
Zero. Fine. So he created a brand new temperature scale where there is no heat, it is zero.
Smart.
Therefore, there can be no negative temperatures on his scale.
Nice.
There it is. So that's called the absolute temperature scale, the Kelvin scale, named in his
Kelvin
honor.
scale. So
And that's the scale we use in science and in engineering typically.
Now, wait a minute. So here's what I'm curious, though. If there is no heat at all, first of all, you have to go someplace where there is no heat.
Or create it, yes.
Oh, okay. So now that's my next question. How do you create a place where there is no heat? Because everywhere on Earth there's heat.
That's really hard to do, it turns out. And so, in fact, initially it was just sort of a theoretical limit of you sort of approach it asymptotically, never actually reaching that point. But I'll get back to that in a minute. So the Celsius scale, named after Anders Celsius, which put 100 degrees at boiling water, 0 degrees at freezing water, and everything else came along the way there. Because to him, why not put 0 at freezing water? But of course you can be colder than that. Therefore, you got to introduce negative temperature. Okay? So the Kelvin scale was developed after the Celsius scale. Celsius scale was originally, or commonly, is also called the centigrade. Centigrades. Centi as in 100th. A degree is 100th of the 0 to 100 from boiling to freezing to boiling. Anyhow, so the Celsius scale already existed. So he said, let me not rock the boat. Let me put 0 at the coldest point, but have each interval of temperature be the same as the Celsius scale.
Okay.
Okay, so no fancy conversions. You just subtract.
Yeah, basically, yeah. And then before you know it, you're really measuring Kelvin in terms of Celsius.
Yes, using the Celsius unit.
Right.
So you can now ask, what temperature is absolute 0 on the Celsius scale?
Gotcha.
You can do that. So you go below 0, and it's way colder than freezing water. You just keep going and going and going, and it's 273 degrees below 0 on the Celsius scale.
So minus 273 Celsius is 0 degrees Kelvin.
Correct.
Absolute 0.
And that's all you got to do.
That's so cool.
So there we have absolute 0. So now the question is, how do you get there? Okay?
Right.
And so it's all about the removal of thermal energy. What is thermal energy? It's the vibration of particles.
Gotcha.
All right? So if you have something that has a higher temperature than some other thing, and you go in and measure the particles and how they're moving, they're vibrating faster.
Gotcha.
Okay, so temperature is the average kinetic energy of vibrating particles in any substance at all.
Okay.
So everything vibrates. So you can have a
vibrates.
solid hunk of iron.
Right.
Does it have temperature? Yes. Then you get in there and you'll see the iron atoms are vibrating. Okay, within whatever lattice they're located, they're vibrating. Now, there's another layer here I'm not going to get into, but I will say it. Okay? All the particles, especially in a gas, all the particles are not vibrating at the same rate. Some are faster than others, some are slower than others. Okay? And there's and the distribution of these has a name. It's called a Maxwellian distribution, named after James Clerk Maxwell, who studied the distribution of the vibration of particles depending on what temperature they were. All right? But as you raise the temperature, all the vibratory speeds get higher.
There you go. Okay.
Okay. So it's why, for example, when you're boiling water and some water evaporates off the top, how come the entire pot doesn't evaporate all at once?
Right.
Okay. Only the fastest moving particles will vibrate. Will jump out.
Gotcha.
Okay. At any given moment, it's only the fastest ones getting out, and all the rest are still in there. And then others populate the fast zone, and then they get out. So there's a range of speeds over which the particles vibrate. Now, a subtle and very physicsy point I have to make. Heat energy is the total energy carried by all the particles.
Gotcha.
Okay? The total energy.
That makes sense.
The temperature, however, is the average kinetic energy of the particles.
Okay.
So, in other words, a cup of coffee, hot coffee in the morning, is hotter than the ocean. However, the ocean has more total energy in it.
Right, because it's the total sum of all the particles.
So it's total sum of all the particles. So I
Gotcha.
just want to distinguish sort of temperature and thermal energy. There's a distinction between those two.
That makes sense.
All right.
Okay.
So let's get back to Kelvin. All right. So how do I make something colder? So what I have to do is I need something else next to it that can take the heat away. Okay? I put food in your refrigerator. The air around the food is colder than the food, has less heat energy than your food does, so it's taking the heat energy from it. Okay? Then what does it do with it? It goes through your coils in the back of the refrigerator, and then if you ever hang out in the back of your refrigerator, it's hot there.
Absolutely.
That heat used to be in the food that you put in it.
Right.
That's where that came from.
See, now what we should do, instead of having an oven beneath our stove, we should have a refrigerator and use the heat to cook on top. And that would make sense.
It doesn't get that hot. I don't know what you put in your refrigerator. So it means you need something colder, something with sort of less heat energy attached to the one that has more, so that it can basically extract it. Well, let's keep doing this. And you keep doing it. Let's get down to 100 degrees Kelvin and 50 degrees Kelvin and 10 degrees Kelvin. I keep doing this, and I'm at 1 degree Kelvin. I need something colder than that. I need something colder to pull away that heat.
Right.
But if I always need something colder, how am I ever going to get to zero?
Yes.
This is the challenge. Okay. So now it turns out you can take a gas, which is vibrating, okay, at a certain rate, and expand it. And that will slow down the vibration of the particles, and the gas will cool. You have to put energy to do that, but you can do that. By the way, that's how compressors work. Point is, you can make things colder, a gas colder, by expanding it. You just keep doing this, okay? You keep doing it. So we can get to within micro degrees of absolute zero. But you can never, philosophically and theoretically, you can never actually get to absolute zero for this reason.
Right.
Because you need something colder than that for it to hit.
Right,
okay.
exactly.
You can get arbitrarily close. Now, there's another problem.
Uh-oh.
Okay?
Okay.
There's another problem. Okay? Quantum physics takes over. And in quantum physics, one of the tenets is you can never know precisely where a particle
Anything
is.
about anything. I believe I read that is quantum physics. You can never know anything about anything.
It's not that bad. Okay. The point is, it means in quantum physics, nothing is ever stationary.
Oh.
So it means there's an entire branch of physics that says you may try to stop the motion of this particle, but you will never succeed. Because there's a quantum vibration that goes on no matter how much heat you've taken out. And this is quantum physics taking over. So the point is, not only is there sort of a classical physical limit to reaching absolute zero, there's a quantum limit that prevents it entirely.
Wow.
And so there it is. A little bit, probably more than you care to know about absolute zero.
No, that's fascinating stuff. That's very cool because you hear about it. I mean, listen, everybody learns about absolute zero in school, but you don't learn about it to the extent that
Not
we
to the
just
extent.
did.
Let me add one other thing.
Go ahead.
Okay. So this is just so cool. All right, but I'll let you to be the judge.
All right.
All right. As a particle slows down, you heard in quantum physics you can have wave and particle duality. You might have heard about that.
That's light.
But of course, okay.
I believe Lord Kelvin may have told me this one.
This is actually Schrodinger showed us that you can have a particle that also functions as a wave. Now, here's the thing. As you slow down the particle,
Right.
the wave associated with it gets longer.
Oh.
Okay?
Cool.
Now, watch what happens. If you have a system of particles and you begin to slow them down and their waves become longer, there's a point where all their waves match up. And the material becomes a coherent, functioning new state of matter.
Really?
And it's called Bose-Einstein condensate. And so this was predicted that if you froze something enough, these free particles, froze them enough, and there they are doing their own thing, doing their own vibratory dance. If you get it cold enough, all of the wavelengths will begin to match. And then the entire substance will function as though it's one object.
Nice.
It's a whole new state and behavior of matter. And it happens at those very cold temperatures, below 1 degree Kelvin.
So you can shapeshift matter?
Yes.
Holy
I love
crap.
that, shape-shifting it. Yes. And
That's
it all happens
unbelievable.
together. And you warm it up, then it goes back to, you know what it's like? It's like birds that flock.
Right.
And then they come down and then they're pecking away separately. And then they start flying, then they all go together.
Yeah, that movie scared the hell out of me. Exactly. Yes.
So it's a bad analogy, but it's visually similar.
Yeah.
Okay?
Yeah.
It's not physically similar, just visually similar.
Wow.
So cool things happen at low temperature. You get superconducting fluids. You get super. You know what super fluidity is? When you cool something enough, and once again you get these wavelengths that match up. And if it's in a fluid state, you can plunge your hand through the fluid, and the fluid just parts in front of your hand, and there is no resistance to moving through the liquid.
Wow.
It's called a superfluid.
Super
This is another quantum state that arises. Then you have superconductivity, where there's no resistance to the current of electricity.
So if you filled a tube with superfluid and there's zero resistance,
Correct.
you could actually travel in that tube at enormous speeds.
Yeah, you can travel faster than the speed of sound in the normal speed of sound in a liquid. That's correct. Yes.
Oh, cool.
Yeah, it's very, very cool. And so it's interesting. Imagine being a funder and some physicist says, I want to play with cold temperatures. And you say, what's the point of that? What are you going to learn? It's just going to get cold. And then you realize that matter behaves completely differently under those conditions. And different matter behaves differently from other matter. And so it is, it's an extraordinary new place to visit in the world of physics. And who ordered that? Who would have thought that this was laying there waiting to be discovered? But it was.
That's amazing. And all I can say is this. As a black man, I do not like the cold, but you have just changed my entire outlook on it.
You're going to visit because you want to get some of that superfluid. That's what you want. And also, the Kelvin, as a unit of temperature, has been elevated to be its own unit without even having to mention the word degree.
It's just the Kelvin.
Well, no, it's not even It's what's the temperature?
29 Kelvin.
Kelvins, that's right.
Oh, Kelvins.
And it is elevated so high that it's now a lowercase k.
Wow.
That's how you know you're bad.
Well, that's when you know you made it.
Right.
Yeah. Exactly.
It's not Kelvin degrees
Right.
Kelvin. It's Kelvins.
Just Kelvins.
It's
Nice.
And you know who else has that? Newton. The newtons is a unit of force. So
Nice.
it's
All right.
just
So,
Newton's
what would you want to be measured? And I know we got to go. We don't. But I just want to end on something weird and fun. What would you want to be measured that would be measured in Tysons?
Ooh. I got to think about that. Let me think about that. I don't have an
It's
answer
a good
right
one,
now.
right?
Yeah, but actually, I don't want to be remembered for anything. I just want to. For me, education is empowering you to understand what it is you're talking about with any reference back to me at all, but thereby you take ownership of your own enlightenment.
See, that's too damn noble. See,
I'm just saying.
I want you to remember me.
Okay, we'll work on what unit will be called the nice. All right, dude, we got to call it quits there.
All righty.
More than you ever cared to know about the Kelvin and absolute zero temperature scale. This is StarTalk, yet another explainer video. Chuck, always good to have you.
Always a pleasure.
As always, keep looking up.